All right, I think we'll go ahead and get started. So welcome back from the break. Hopefully you had a nice break, relaxing. We're up the home stretch. So in the previous lecture, we started talking about how we can train single layer neural networks. I guess a couple of variants of gradient descent. So the main one being stochastic gradient descent, SGD. And then as part of this assignment, you're implementing stochastic gradient descent or gradient descent on some toy kind of data sets. And yeah, just to remind you that the form of a single layer neural network is something like this. So we have an input, for example, an image. You multiply that with a weight vector, add in a bias term potentially, and then pass that through a nonlinear function, like a tan hyperbolic function, or a sigmoid, a Rayleigh function, and so on. And the way we were doing this training of W and B, the way we were choosing W and B, was to use stochastic gradient descent or gradient descent to minimize the training loss. So this is the average loss on the capital N training examples that we have access to. So for each input, xi, we make a prediction. So this is the predicted label. And then we compare that with the true label, yi. And then we average all of those losses across the different examples. And we looked at some examples of different losses. The simplest one just being like a binary correct or not correct loss. And then we saw some of the challenges with that. And then we looked at the binary cross-entropy loss, which is what you're using as part of this assignment. And then we started looking at how we can go beyond single-layer networks to multi-layer networks. So this was just at the very end of the lecture, so that's where we're going to pick up today. So I'll say much more about multi-layer networks, what they look like, some theoretical results associated with them, and some practical challenges as well. So let me just open up the slides here. Okay, so all the inputs here are going to be very low dimensional, in particular two-dimensional, so we can visualize everything. So this, I guess, can everyone see? Maybe just raise your hand at the back if you can't see things clearly, the text. Okay. All right, so this here is the domain in which all the inputs live. So each point here is a particular x. And we're going to, like this visualization here is a visualization of the neural network. So we're going to begin with 0 hidden layers, which corresponds to just a single layer neural network. I'm going to choose, I guess, one of these data sets, let's say this one, and let me just reduce the noise here. Okay, so the orange and blue clusters are different classes. Here the class labels are -1 and 1 instead of 0 and 1. So the orange is -1, the blue is +1. And I guess the options here, so the learning rate, that's that determines the step size at every iteration of stochastic gradient descent. There's a batch size of 10, so that's how many samples you use in every update for a stochastic gradient descent. Tan H, that's the nonlinearity we're using. Ignore these for now, we'll come back to it in a bit. Okay, so that's what happens in this data set. So this is a data set of maybe like 100 or so examples. And pretty much immediately the training loss, which is visualized over here. So ignore the test loss for now, just focus on the training loss. The training loss pretty much immediately goes to 0. So let me just play that again. So this is running stochastic gradient descent kind of in real time. in your browser. Okay, so yeah, so you can see that the decision boundary, so that's the boundary between orange and blue, separates the classes pretty much perfectly in just a few steps of gradient descent. So this is the simple case. This is the case where we expect a single layer neural network to work. Here are some more interesting cases. This is one where a linear decision boundary fundamentally cannot separate the classes. You can maybe try different linear boundaries and see that there isn't one that works to separate the classes. So stochastic gradient descent is going to find something. And you can see that the training loss is pretty high, right? So it's close to almost like 0.5. So it's classifying kind of half the examples correctly, the other half incorrectly. So it's finding something, but you can see that it's not correct. There's orange stuff on this side, but there's also orange stuff on this side. And then some other examples. This is another one where there's no linear decision boundary that separates the two classes. And again, it's basically just finding something that has a training loss of 0.5. So it's classifying half of the examples correctly, the other half incorrectly. So this, I guess, motivates, we saw some of these examples in previous lectures. This motivates the need to have a richer function class, something that doesn't just have a linear decision boundary, but a more complex decision boundary, which we can get by adding hidden layers. So let me start with one hidden layer on this example. So you can see that it starts to do something more interesting. So the boundary between orange and blue is no longer linear, because now the space of functions that we're optimizing is nonlinear. It's still not able to perfectly separate the two classes, so the training loss is lower than it was before, so it's lower than 0.5, it's about 0.18. So we can make the dimension of the hidden layer larger. So I'll make it 6-dimensional. And now you see that it's able to get the training loss to 0 pretty much, or close to 0, and I'll go down to 0. Question?
So is every layer like a degree, like a polynomial?
Yeah.
The first one was straight and the second one?
Yeah, so it's not quite a polynomial because the nonlinearities are like, I guess, don't keep the function space polynomial, but yeah, it's sort of like a degree. So if you chose the nonlinearity, maybe in a specific way, you could get out polynomials. But yeah, it's essentially adding more and more nonlinearity as you add more hidden layers. Yeah, good question. Other questions on this? Go ahead.
What are the small squares next to the...
Good, yeah. So the small squares are visualizing what each neuron is doing. So each of these neurons is taking the 2-dimensional inputs, so x1 and x2, and each neuron is itself like a single layer. You can think of it as a single layer neural network, like it's doing, I guess, the sigma W transpose x plus b, but where x is whatever the kind of previous input was. So going from here to here, we're doing sigma W transpose x plus b, and then to go from here, the hidden layer, to here, we're taking these as the input and passing that through a single layer. So this is kind of visualizing what each of these neurons is doing. So each one has some linear decision boundary associated with it. So that's what they're visualizing here. Yep, good question. Yeah, so you can see that the training loss, I guess, as we were answering questions, went down to 0. We can do this for some of the other examples as well, so let's try this one. And again, you can see that the training loss is going down to 0, so it's able to pretty much perfectly separate the two classes, orange and blue. Maybe there's one more we can try the spiral one. So this one's a bit more challenging. It's going down, but pretty slowly. There we go, and now it's quick. Yeah, and I guess this shows you, I think it'll converge to something that's not going to perfectly classify everything. So it seems like it's close to convergence here. So it's doing something, right? Like it's kind of getting the blue here, it's getting the orange here, but it's misclassifying. Actually, it's not misclassifying. Yeah, I guess it's misclassifying some of these points over here, but it's doing a reasonable job, definitely better than 0.5. So we can increase the complexity of our function class, add another hidden layer, and see what happens. So it seems better. It's getting, the training loss is 0.078, which is lower than it was. It's basically getting everything. There's some blue points here that it's misclassifying as orange. So maybe we can try just one more, increase the, I guess 8 is the maximum. There we go, pretty much almost there, just that last little bit. Yeah, so it gets the spiral pretty much exactly. Go ahead.
So I noticed that the sign function is a option of a feature, an input feature. I'm wondering, is it often the case that periodic functions are chosen perhaps as an activation for layers, or is that not common?
It's uncommon. Yeah, it's pretty uncommon to choose periodic functions. So actually, sorry, I guess we should be careful here. So did you mean these?
But sometimes I assume you can also use a sign function as an activation.
As an activation function. Yeah, so sign is, yeah, so it's not an option here, but you could, yeah, you could use it. It's not that common. I don't remember an example where there's like a,
You can use it for PDE. Like,
potentially, yeah. Maybe if there's some like inherent like periodicity like baked into your data, that might be a good reason to use it. Yeah. Yeah, good question. Okay, yeah, question.
So are we minimizing the training loss at each layer, at each neuron, or where is that?
Yeah.
occurring?
Okay, good. Yeah, I'll talk about that. Yeah, I'll talk about that actually as the next thing. So let me switch back to the blackboard. Yeah, so I guess the short answer is that we're gonna minimize the overall training loss. So instead of using a single layer network here to make a prediction, we're going to use a multi-layer network. And yeah, I guess the picture to have in your head is that we start with the input. We process that through a bunch of single layer networks until we get to the output y, which potentially could be itself a vector, or it could be a scalar, depending on the problem. And each of these corresponds to the hidden layer. So the actual computation is as follows. So you start with the input x, and you pass that, so you multiply that with some matrix, W1, you add in a bias term, B1, and you pass that through a nonlinearity. And then you keep doing this. So H2 is sigma W2, and now you pass in the H1 instead of X to this layer. H3 is the same thing, where you pass in H2 as the input to this layer, and so on. So let's say HD, D for depth, is W D, H D minus 1 plus B D, and then finally you get to the output layer. As follows. So that's the general kind of computation corresponding to a multi-layer network. What I've drawn over or written over here is called a multi-layer perceptron. So without imposing any further structure on the matrices W, this thing is called the multilayer perceptron. We'll talk about how to make maybe better or different choices for the structure of W in the next lecture. And I guess just a couple of notes. So each dimension here, so each HI is a vector. Right, so each hidden layer is outputting a vector, and the kind of number of neurons in the TensorFlow playground corresponded to the number of dimensions in each intermediate representation. So each HI belongs to R Ni, and the dimension Ni is determined by the matrix dimensions, so W1, W2, and so on. So each HI is sigma Wi, HI minus 1 plus Bi. So Wi has dimension Ni times Ni minus 1. HI has dimension HI minus 1 has dimension Ni minus 1 times 1, and then Bi has dimension Ni times 1. So you can think of Bi as a column vector. So this gives you Ni by 1, and that's the dimension of HI. And you can have like potentially different dimensions for each of the hidden representations until you get to the output layer. And I guess the other note is that sigma is applied element-wise. So sigma again is the nonlinearity. So sigma is always going to be a scalar function. So it takes in a scalar, outputs a scalar. So you apply sigma to each dimension of HI separately. So at the end, not each dimension of HI, each dimension of W HI minus 1 plus Vi. This is a vector, so you apply sigma to each element separately. And at the end you get a vector of Ni by 1. I guess any questions on this general computation? Okay, so yeah, actually before talking about the training, I think one natural question is how many layers do we need? Like how many of these, like what should D be? Like what should the depth of the network be? And what should the dimensions of these intermediate layers be? So there are some kind of theoretical results that give you some useful information. I don't want to kind of oversell this. I think these results are like good to know about. They're not necessarily that useful in practice, but it's just like good to know about them. So they're basically these universal approximation theorems. So I'll present just one, and I'll mention some variants of it. So let's say your function class. So these are the set of functions that are defined by this kind of structure. So each function I'll call like fnn. So it takes in an input x, which is a vector, and I'm just going to define this to be w2 sigma w1 times x. So this is a pretty restricted version of the more general thing that I wrote down here. So all you're doing here is taking the x, multiplying that by a matrix w1, applying element-wise nonlinearity sigma, and then taking the output of that and multiplying that by w2. So these are nonlinear functions, or you could represent nonlinear functions using this kind of architecture because sigma is nonlinear. So the result, that, let me just actually, I guess, set up some more notation. So let capital X be some bounded subset of the space of inputs. So some compact set of subset of the domain, which is the space of inputs, and let F, and let's say that the space of inputs is R nx. So nx is the dimension of the input space. And let F be some continuous function. From the space of inputs, which has dimension nx, to the space of labels, which has some dimension, which I'm calling ny. So the result, so this universal approximation theorem, or I guess one of these universal approximation theorems, states that for any value of epsilon, which is greater than 0, there exists W1, or exist W1 and W2, such that f of x minus f and n of x, and this is some norm. So let's say it's the 2 norm. It doesn't matter that much. Is less than epsilon for all x in this bounded domain, this bounded subset, which we're calling capital X. So yeah, I guess just intuitively in pictures, what this is saying. So imagine that x is a scalar, y is a scalar. We're choosing some bounded domain of x's, and we have some continuous function that's defined on this domain. So it looks like this. What this result is saying is that for any tolerance that you pick, so any epsilon greater than 0 that you pick, you can find choices of W1 and W2 such that the resulting function, f and n, which I wrote up there, approximates this continuous function, any arbitrary continuous function, within this threshold. So let's say like f and n maybe looks something like this. So the solid line, let's say, is f, and the dashed line is f and n. And the difference, so the largest difference is less than epsilon over this bounded domain that we're looking at. So I guess any questions on this? Go ahead.
How does overfitting fit to that? Wouldn't that be overfitting?
Yes, good question. So this is basically saying that we can overfit. So that we can, so for any, well, okay, so I guess that's one interpretation of it, that you can overfit. Another interpretation is that whatever the true underlying function is, so let's say f is the function that like actually underlies your data, like your true data, maybe even that you don't have access to. So f is the actual mapping from inputs to labels. Then there exists some neural network of that pretty restricted form that will arbitrarily well approximate that function f on whatever like bounded domain that you choose. Question?
Is the hidden dimension bounded in this data?
Okay, good. Yeah, so that was going to be, I guess, the next comment I make. So the hidden dimension is not bounded. So I don't know if I gave the name to the hidden dimension, but so the output of sigma W1x can be can be arbitrarily large. So this is not saying that there exists some it's not providing any bounds on the dimensions of W1 and W2. It's just saying that there exists some, and it could be absurdly large.
Goes to infinity of the complexity of that.
Exactly. Yeah. For any fixed function and fixed domain, there's going to be some finite dimensional W1 and W2. But yeah, as you make F more and more complicated, more like wiggly, maybe basically have a large curvature in a bunch of places. The complexity of F and N, as kind of measured by the dimensions of W1 and W2, could grow to infinity. Yeah. Good. Other questions on the result? Okay, so I think, like I said, this is useful to know about because it gives you some theoretical justification for looking at functions of this form. So if this property wasn't satisfied, then maybe you would be slightly concerned potentially that this is not a good class of functions to look at. But like I said, I don't want to, oversell the importance of this result for a couple of reasons. So actually, before that, let me just make another note. So what I presented here, the depth is fixed. So we just have basically one hidden layer. There's a similar result for bounded width. So if you constrain the dimensions of the intermediate representations, if you constrain the dimensions of W1 and W2, but allow the depth to go to infinity. So the number of, I just erased it, but the number, the dimension D, or not the dimension D, the value of D that you allow, the number of single layer operations that you do, if you allow that to grow to infinity, there's a similar result, like this universal approximation result. So similar result for bounded width, but arbitrary depth. Yeah, and just to emphasize what I was saying before, so there are other function classes. So for example, polynomials or trigonometric polynomials that also satisfy this universal approximation. So for any continuous function on a bounded domain, you can approximate that function with polynomials of potentially high degree. So there's nothing really that special in terms of the theoretical result about multilayer perceptrons. So there's other function classes that also satisfy these results. So in practice, the reason we see multilayer perceptrons used for deep learning rather than polynomials, for instance. So someone's trying to use polynomials for computer vision. I think that the main reason is a really empirical one. So in practice, main reason for neural networks, like multilayer neural networks, is that these function classes seem to capture the structure of real-world data or functions. So like I said, the universal approximation theorem, it's good to know about. Like it gives you some theoretical justification for using multi-layer perceptrons, but the main reason really is that the kinds of functions that we encounter in practice, so for example, in computer vision or in other applications like natural language processing, it seems like these architectures, like these function classes, do a pretty good job of like compactly representing those function classes that actually do arise in practice. So I think that's the real reason we use them, not so much because of this universal approximation theorem. But yeah, I guess historically, so I don't remember exactly when these were proved, maybe in the 70s or 80s. This had some like historical, like it served as some kind of like motivation, like historically, for looking at these function classes. But yeah, I guess nowadays no one pays that much attention to them. It's mostly just that these things work well in practice, and that's why we use them. Yeah, I guess any questions on the result? Okay, so yeah, let's get back to your question. Well, it's a question about training these multilayer networks. So the question here is, how do we choose the weight matrices like W1 through WD and the bias vectors? And we're going to do the same thing as we did for single layer networks. So we're going to minimize the training loss. Using stochastic gradient descent. Or one of its variants. So the training loss in this case, we're going to denote by L again, which is, we can think of as a function of the weight matrices and the bias vectors. So how many of these you have just depends on the specific like depth and yeah, I guess the specific depth that you choose. So we're going to define the training loss to be, again, just the average loss over our capital N training examples. Where yi predicted now depends on like our choice of the weights and the biases. So yi predicted, I guess I erased the specific form, but like yi predicted takes in xi as input, passes it through each of these like single layer computations until you get the label out. So this depends on W1, W2, and the biases. So yeah, I guess what we're doing is looking at the kind of end-to-end loss on our training data set and choosing W1 and W2 and the biases to minimize this average training loss on this average loss on our training data set. So yeah, I guess the question is, how do we do this minimization? How do we apply stochastic gradient descent? So if we're doing gradient descent, and also if we're doing stochastic gradient descent, what we have to do is take each weight or bias, so each W or B, and update it by moving in the direction of the negative of the gradient. So gamma again is the step size, and yeah, we look at the gradient of the training loss. With respect to W1, multiply that by the learning rate gamma, and then take a step in the direction that's opposite to that gradient. And then we do the same thing for the other parameters. And then the same thing for the biases as well. And yeah, I guess what I'm writing here is are the set of computations that we do at each step of gradient descent. So at each step of gradient descent, we look at the training loss, or if we're doing stochastic gradient descent, we look at the training loss on some subset of our data. We look at the gradient with respect to the different parameters, the different weights and biases, and for each one, we take a step in the direction that's minus of the gradient. I guess here I'm choosing a single learning rate for all of the weights and biases. In principle, you could choose different learning rates as well. Question?
So is the difference between the neurons that we're initializing them differently?
Say that one more time, sorry.
Is the difference between the neurons that we're initializing them differently, which is how we're combining them?
So we are going to be initializing them. Yeah, I guess I didn't write the initialization set. Typically, you just take some like random initialization. So that part is right. I guess I'm not sure I followed the difference in the neurons part.
We have a number of neurons, and what's making each of them distinct and providing?
Okay. So they don't necessarily have to be distinct, right? So we're just choosing some setting of them that minimizes our training loss. And it could be that you end up with, I guess, neurons that are similar or the same. But yeah, in practice you wouldn't, because we would just initialize like each of the W's and B's randomly. Yep. Yeah, typically it's like you choose, there's like various kind of clever initialization schemes, but the simple ones where you initialize them to be something close to 0 at random.
So like layer 1 corresponds to W1, layer 2, W2?
Yes, exactly. Yeah.
So then, so each neuron makes up the weight. You could think of it that way. So if we have like 5 neurons per layer,
yeah.
How does each neuron come into this representation?
Yeah, so I guess we haven't really been super careful about defining what a neuron is. Okay. I think it's easier to think about just hidden layers and hidden representations. You can think of a neuron as one component, like each dimension of a hidden representation, like of the HIs, you can think of as a neuron. Yeah, I guess that's typically how one thinks of them. But yeah, I think it's easier just to think about this kind of processing. Let me just draw it out here, where you start with the input, you apply like a single layer computation to it, so you get some hidden representation H1, and then do the similar computation again, and then all the way up to HD, and then finally to the label. So each of these is a hidden layer, and then each H1, H2, up to HD is a hidden representation. And yeah, I guess as I was saying, each dimension of that, each element of that, you can think of as a neuron. Good. Other questions? Okay, so I guess the thing we need to do to actually implement stochastic gradient descent is calculate the gradients. So I'll just briefly mention how one can do this. computing the gradients that we need to apply that algorithm. So the technique to do this is what's known as back propagation, which is really just the chain rule. It's a fancier name for the chain rule. So to see how this works, let's look at a kind of restricted class of functions. So it's the same kind of class of functions that we were looking at for the universal approximation result. So we're going to ignore the biases here, and there's basically just one hidden layer. So in this case, the training loss is just a function of W1 and W2. And again, the predictions for each input depend on the choices of W1 and W2. So what we need to calculate is the gradient of the training loss with respect to W1 and the gradient of the training loss with respect to W2. So yeah, we're going to use the chain rule. So we're going to first calculate the gradient of the y prediction with respect, or yeah, gradient of y with respect to this hidden representation. So let me write it out here. So W is W1, sorry, y is W2, sigma W1 x. So this sigma W1x, so let's call that H. So we can calculate the gradient of the loss L. So that's the little, oh wait, sorry, I forgot the L. So that's the loss for each example. So we can calculate the gradient of L with respect to yi predicted. So that's a relatively simple calculation because the loss here is just something like the binary cross entropy loss. So we can just calculate what that gradient is. And then we can calculate the gradient of yi predicted with respect to W1 and W2. So for the second part, like calculating the gradient with respect to W1 and W2, that's where the chain rule comes in. So I'll do it in terms of partial derivatives, so that's the kind of transpose. So partial y, partial w2. So if we're looking at the partial with respect to w2, that's just h, I guess transposed by convention, and then the partial So that's the first part, so calculating the gradient of the partial with respect to W1, and then partial with respect to W2. So we can look at partial y, actually sorry, I missed W2. So the W2 times partial y, partial h, and then partial h. Partial W1. So this is the chain rule. So yeah, if you think of this architecture as having one hidden representation H, so we're starting with the input going to H and then going to Y. The reason it's called backpropagation is that we kind of work backwards. So we look at the gradient of the label with respect to the hidden representation H, and then we look at the gradient of the hidden representation H with respect to the weight W1. And if we had, so what we're asking is if I perturb H a little bit, how does the label change? And then if I perturb X a little bit, how does the hidden representation change? And if you have like multiple layers, you kind of work backwards from the label all the way up to the input. So that's where the name backpropagation comes in. But it's basically just the chain rule, right? We're just calculating the gradients using the chain rule, the gradients of the loss, the training loss, with respect to each of our parameters, like each of the weights and biases. In practice, I guess it's good to maybe work through this and make sure you understand why it's just the chain rule and exactly how it works. In practice, there's like software libraries, which I'll mention in the next lecture, which do this gradient computation very, very efficiently and completely automatically for standard kind of neural network architectures and losses and so on. So yeah, I guess backpropagation, people sort of realized that you could use it to train multi-layer networks back in the 1980s or so. And I guess a couple of different researchers like rediscovered it. And this is the main kind of workhorse, like algorithmic workhorse. This combined with stochastic gradient descent for training neural networks today. Yeah, I guess any questions on the training part? So did I answer your question? All right, other questions? Okay. All right, so that's the training part. So far, we've kind of focused on the story of finding weights and biases that minimize our training loss. But I guess as we've mentioned before, we don't really explicitly care about minimizing the training loss. Like for our training data set, we already know what the labels are. What we really care about is not the training loss, but the test loss. So on examples that are not part of our training data set, how well can we predict the labels? And that's where overfitting comes in, which we mentioned previously, and I guess we'll spend a bit more time discussing now. So let's go back to the tensor board. Okay, yeah, and I realized I left the gradient descent running for that example. So it's, yeah, the training loss is exactly, or like pretty much exactly 0, and it's captured the spiral pretty nicely. Okay, so yeah, let's look at this data set over here. So this is the one where a single layer network can perfectly separate the two classes in training. The one sort of difference I'm going to introduce is adding a bit of noise on the examples. So what this is doing is basically just smearing the data a little bit, such that there's no one kind of linear classifier, like one linear decision boundary that's going to perfectly separate the orange from the blue. So if you pick something over here, there's going to be some small fraction of the training data that you misclassify. And I'm going to just have one hidden layer with 6 neurons, so 6-dimensional hidden representation. And I'll keep all the other parameters the same. So I guess what I want you to focus on is the difference between the training loss and the test loss. So the training loss is what we're familiar with, so that's just the average loss in our training data set. The test loss is being calculated by giving the trained neural network examples that are not part of the training data set and evaluating the loss on those kind of unseen examples. Okay. Yeah, so what we see is that, so the training loss is kind of going down nicely. So 0.094 or 0.93. And yeah, I guess we're seeing that it's not finding a linear decision boundary. So we're using one hidden layer so we can represent kind of nonlinear functions, and it's using that nonlinearity, right? So it's bending the decision boundary, which is where the function is 0, to sort of try to distinguish between these examples that are kind of in this like boundary between orange and blue. So it's making the function more and more complicated as we do the training. So let's make it even more interesting. So I'll add one more hidden layer with, again, 6 dimensions. And again, just keep an eye out on the difference in the training loss and the test loss. So again, the training loss is going down. So that's what we're minimizing using stochastic gradient descent. And what's interesting is that the test loss is going up after a while. So it's 0.14, 1.5, and so on. So even though we're minimizing the training loss, we're doing a good job separating the training examples really well, but yeah, on unseen examples, we're not doing so well. In fact, as we decrease the training loss more and more, we're doing worse and worse on the thing that we actually care about, which is the test loss. So I guess just to show you that this is not specific to this data set, so let's go to this data set. Again, I'll use 2 hidden layers with 6 neurons each. And again, just keep an eye out. I guess you can read the text, right? Okay, good. Yeah, so keep an eye out on the training loss and the test loss. Again, we see that the training loss is going down as we expect. That's the thing that we're minimizing. But the test loss is actually going up by quite a bit. So if you look at the curves here, so initially you see that as the training loss goes down, the test loss also goes down. So the training loss is gray, the test loss is the black curve. So initially they both go down, but then after a while, the training loss still keeps going down, but the test loss starts to increase. So I guess this is what's known as overfitting. So we're overfitting to the finite number of training examples that we have access to. And yeah, you can see that it's kind of making the decision boundary more and more complicated as the number of steps of stochastic gradient descent increase. Yeah, I guess any questions on this phenomenon? Okay, so yeah, so the question is, how do we prevent overfitting? I'm going to use the TensorFlow playground again, so let me try to write over here. So there are basically 2 approaches, or 2 kind of classes of approaches for preventing overfitting. Intuitively, the way to think about how we can prevent overfitting is Occam's razor. So this is just intuition. So if we have multiple functions that all fit our data kind of equally well, so let's say that all have a equal training loss, what we want to do is pick the function that is the simplest in some sense. So we have to define what simplest means. So I'll just kind of write a short version of this. So choose, so I guess among functions that all fit our data, so our training data equally well. So equally well as defined according to our training loss. So you want to pick the one that is the simplest. And you can kind of see that the function that we're picking just by minimizing the training loss is not particularly simple, right? And you can see that by looking at the complexity of the decision boundary. So it's trying like really, really hard to perfectly classify all the examples in our training data set, and we're giving up. We're doing that well, but we're giving up on the test loss, which is what we really care about. So I guess with this intuition of Occam's razor, there are two approaches or two classes of approaches that you can use to prevent overfitting. So the first one is what's known as regularization. So basically adding something to the loss, so adding some term to the loss function that promotes simplicity. Simplicity as kind of formally we'll define in just a second. The other class is to basically choose a neural network architecture more kind of cleverly based on some knowledge that we have about our data generating process. So this one we'll spend more time talking about in the next lecture. But the basic idea is to choose architectures that reduce the number of decision variables, so the number of parameters that we're fitting. Here we're saying like W1, W2, and the biases can be pretty much arbitrary, but we're going to add a bit, or we can add a bit more structure. We can say that maybe some of the elements of the weights and biases need to be 0, and there's only some elements that are going to be non-zero, so that reduces the complexity of the function class that we're using. So by choosing a kind of more judicious architecture, we can potentially kind of get around this problem of overfitting. So let's talk about the regularization one, and then we'll see an example of this in the TensorFlow playground. So with regularization, what we do is minimize not just the training loss, but the training loss plus an additional term that's known as the regularizer. So let's say the training loss we still denote as L. So we think of this again as a function of the weights and biases. What we're going to do is add another term where lambda is going to be a scalar parameter that basically says how much regularization to apply, multiplied by, so this is one particular choice. So multiplying by the summation of the norm squared of all our decision variables. And so on. So we look at each of our weight matrices, each of our bias matrices. We look at each element and square it, add them up. And so this is just a scalar. This whole thing is a scalar, which is a function of the weights and biases. and then we multiply that by some lambda. So if lambda is 0, then we're just minimizing the training loss. If we increase lambda, what we're saying is choose W's and B's, like choose weights and biases that have a small norm. So we're basically biasing our choice of W and B to things that are closer to 0. So there's nothing kind of really fundamental about 0. You can think of this as just making the function class more simple implicitly. We're not like explicitly reducing the number of parameters. We're just saying like try to find something that's close to 0 in terms of the weights and biases. So I guess any questions on just the process, like what we're doing over here? Okay, so let's look at an example in the playground. So this is without any regularization. We're just minimizing the training loss. So let's let it run. And maybe I'll just keep track of the training and test loss over here. So without regularization, and then with regularization, training, and the test. So yeah, I guess it depends on how long we let it run. So the training loss, so let's say we stop it over here, is about like 0.213. So without regularization, it's about 0.213. And the test loss, actually, I guess let me write it down, 0.427. And if we run it, we can see that the training loss is going down and the test loss is going up, right? So we're seeing overfitting as we expect. So now if I add L2 regularization, so L2 because we're looking at the 2 norm of these decision matrices and vectors, and I'll add regularization of 0.01, so that's the lambda, the regularization rate. And it's the exact same setup, the same data set, and so on. So we see, I guess what's interesting is that the training loss is still going down, so 0.289, 288, but the test loss is no longer doing what we were seeing it do before, which is go up, right? So the test loss is basically constant at 0.355. So the training loss is 0.288, and the test loss is about 0.355. So I guess what's kind of interesting is that we're doing a worse job of fitting our training data, right? So our training loss previously without regularization was 0.213. Once we add regularization, the training loss is higher, 0.288. It makes sense that it's higher because we're adding an extra term, right? We're not just minimizing the training loss, we're minimizing the training loss plus something that's penalizing the complexity of the function. Question?
Is another strategy to take the derivative of the difference between test loss and training loss and know when to stop?
Yeah, good. So in practice, so the test loss is something that's kind of hidden, right? So the test loss you don't have access to explicitly. It's just like future examples. So here we're like pretending like we have access to the test loss, but some variant of what you said where you have some data set that's finite. You split up that data set into a training data set. Let's say that's 90% of the data set, and then the rest of the 10%, it's what we call the validation data set. And you can basically do this. You can stop the training once the validation loss starts going up. And the validation loss is kind of a proxy for the thing that we really care about, which is the test loss. Yep, good. Yeah, and I guess the punchline here was that the test loss is a fair bit lower, right? So it was 0.427. Without regularization, once we add this regularization, it's 0.355. And we don't have this phenomenon where the test loss is going up. And I guess we can try this with other data sets as well. So maybe let's do this one. So let's switch off the regularization again. So we can see that it's doing some kind of funny stuff, right? It's sort of linear here, but then it's adding a little like island of stuff to capture some of these orange points over here. And again, the same thing is happening where the training loss is going down, but the test loss is going up. So the test loss, 0.175, 176, and it's going to keep going up. And then now if I add in regularizer, so 0.01 again, let's say. Yeah, we can see, even just qualitatively, like it's not making the function as complicated. Like there's no like little island that's appeared. It's basically linear, the sum nonlinearity kind of over here. And the test loss is a fair bit lower. So it's 0.17 something, it's 0.101 with the regularization. And I guess if we crank up the regularization, so if we make it 0.1, let's say, so that's an order of magnitude higher. So the test loss is still about the same, 0.11 or so. But you can see that the function is simpler. So the decision boundary is closer to linear. So that's basically what we're saying, right? Like try to find something that's simpler in the sense of, in this case, the decision boundary being closer to linear. All right. So that's strategy one, I guess, regularization. Other strategy. So typically you'd use kind of both in conjunction with each other. So you'd both regularize and try to find the best neural network architecture that you can find that reduces the number of parameters that you're optimizing for. So we'll say more about that in the next lecture. Any questions on this? So the last assignment is due tonight. We're going to release the final project probably like early tomorrow. So the structure of the project is pretty sort of similar to the RRT lab, so that was the motion planning lab. So it's similar in the sense that the obstacle setups are going to look very similar. So we'll have the red PVC pipe set up in our two spaces, Andlinger and G105. The main difference is that the obstacle locations are going to be unknown to you a priori. So you're kind of going to show up on the demo day. I'll say a bit more about that. And then the obstacles will be placed in some configuration. I guess we always receive questions about this. It's not going to be adversarial, right? We're not going to choose some like really bizarre set of configurations. They're just going to be kind of random-ish locations for the obstacles. We're not trying to like specifically mess up your algorithms. But yeah, I guess the point is that you don't know exactly where the obstacles will be beforehand, so you need to use the cameras and some kind of computer vision to figure out where the obstacles are to then avoid them. We're going to use the same obstacles as the RRT lab, so they're just cylindrical obstacles, the PVC pipes with a known radius, like it's just whatever the pipes are, whatever pipes are like present in the spaces currently. The obstacles are pretty uniformly colored, so that makes some of the computer vision a bit easier. And the goal is basically to get to the other side of the obstacle field and then land near some target object. So the target object is a book that you can bring. So the book has to, I mean, it can't be like some ridiculous book that's like massively large. So we have some like rules on the book. So it's basically just a normal book. You can make some modifications by like changing the cover and so on, but yeah, just a regular book. And then you basically land, so the book will be placed on either like a table, something similar to this, or like a pedestal. It makes it a bit easier to see, like as the drone is flying. If the book is at a similar height to the drone, then it's easier to see. You don't have to land on the table, like you can just land on the ground. And there's going to be points for basically how close you get to the book. And I'll say more about that in a bit. And the evaluation is going to be on like our demo day, which is Dean's Day, December 16th. So we'll send out a sign-up sheet soon, within the next couple of days or so. So I guess each team will sign up for, I think it's a 20-minute time slot, and you can choose based on your schedule, I guess whatever works. And question, sorry.
Is the target known, the location of the target known?
Okay, so the location of the target will not be known. So we're going to place the target just in the kind of end zone of the obstacle. So I guess so X is forward according to our coordinate system for the crazy fly. So in the forward direction, it's kind of known. It'll just be at the end of the course, and we'll just place the obstacle, not the obstacle, the target object laterally in some location.
Would you know the X?
Yeah, roughly, pretty much roughly. Yeah, you know the X direction or the X location. So I guess a few ideas. So we'll provide some starter code for you to get started on the project. So there's a bunch of different options for you to choose from. We're not going to specify a particular approach, so you're free to use whatever approach you want. So I guess principled approaches to this could be to figure out the locations of the obstacles using the camera. So for instance, because the obstacle geometries are known, you could look at the number of pixels that each obstacle spans and then back out the distance based on that. And then once you have the distances, you could use RRTs or PRMs or A-star or any of the kind of planning algorithms that we discussed in this course to do the planning. And the planning probably makes sense to do in a receding horizon kind of fashion. So you plan a little bit, execute some portion of that plan, locate where the obstacles are, replan, and so on. We're also, I guess we've been playing around with some pre-trained neural networks for monocular depth estimations. This has been kind of like, there's been a massive amount of progress on this relatively recently over the last year or two. So with a single image, figuring out depths to the different locations in the scene. They give you relative depth, so it's kind of a scaled depth that you get, not absolute depth. So there's some like tricks to getting the absolute depth from that relative depth. But we'll provide some starter code for that as well if you're interested in playing around with some of these fancy neural networks. It's actually based on transformers, which we'll say a little bit about in the next lecture. Yeah, I guess there's other approaches. You can calculate some or compute some library of trajectories like motion primitives. Move straight, turn left, turn right, and so on, and then apply them kind of sequentially as you see where the obstacles are. Hand-tuned strategies like find like the largest gap and like navigate towards that gap. Those are like perfectly legal as well. And like those kinds of strategies have like worked pretty well in the past. They're kind of relatively simple. There's some like hand tuning, hand specification that goes on. But yeah, that's perfectly fine. And then you can use like the pre-trained neural networks that we use for Lab 8 for localizing the book. And as I mentioned, you can make some modifications to the book. So if you want to like add a cover to the book, like change the color and so on. So that's something you're allowed to do. Grading rubric, this is written out or going to be written out more carefully in the instructions. But the grading is basically going to be in two parts. So one is the collision avoidance part, so there's 80 points for that. And that has to do with the fraction of the course that you traverse before colliding, and then 20 points for landing near the target object. And the landing part is just based on the horizontal distance, and we have some thresholds for the points there. And the final score is the average of the two best trials. So you can have, I guess, one run that's pretty bad. And we often get questions about, like what happens if the drone just does something crazy? So in that case, it's fine. Like if it clearly does something, like the battery kind of gets drained or whatever, then you can just like rerun. We're not going to be like super strict about those kinds of things. Yeah, and as I said, this will be written out a bit more carefully in the instructions. And just some final notes. So as I said, we're not kind of restricting you to a particular approach. You're allowed to use OpenCV in particular. I think it's going to be like super useful, and other software libraries that you're free to choose from. And yeah, you can be creative with the approach as long as it's not something kind of completely silly. Just go straight and hope for the best. Question?
Are the cylindrical obstacles in the one lab where they are able to be moved around?
Oh yeah, definitely. Yeah, so you can move them around. I guess just don't take them home, but yeah, you can move them around. Yeah, and the main piece of advice, as always with anything, is to start early. No one's going to listen to this, but you should, because it's going to be a scramble at the end if you don't start early. So yeah, start early. Other questions on this? Go ahead.
Is there like a certain time when the obstacles in the lab will be up, so we can maybe test it, or?
So they're always around. Yeah, you can test it any time. I think it's like 1 a.m. to 6 a.m. you're not allowed to go in, but any other time. The obstacles should already be there, so yeah. I guess right now you're doing the other lab, so they're not there, but they have like hooks, you can place them. Another question?
Yeah, that was my question.
Yeah.
Which lab we're going to be testing it?
Okay, so what I would recommend, and this is written out as well in the instructions, is pick one space and stick to it, because the lighting conditions can be different, and that can potentially mess up your computer vision algorithm. So just pick one space, stick with it. And all three netted zones are going to be available. So 2 in the Anlinger space and 1 in G105. Yeah. Question?
Do we have access to the downward-facing camera, or is it just?
Yeah, so it's just a forward-facing camera. Unfortunately, there's no way we couldn't figure out how to get access to the optical flow camera. Yeah, that would have been nice, but unfortunately not. Yeah. If you figure it out, I guess let us know, and then we'll use it for next year. Other questions? All right, sounds good. So I'll see you on Thursday.